you're going to be recording.
So we're recording. Yeah, we're recording it and we'll share the recording with people afterwards. Okay, so welcome folks. Thanks for joining Geology of Southwest Oregon. I hope you had a chance to read the Zoom tips. We have some technical challenges this time. We're kind of mixed modality, in person and not in person. I'm here with our instructor, Jad D'Allura, so we're hoping we're not going to get too much feedback. But please keep yourself on mute, and during the presentation, you can turn your video off. We'll have a couple of times for question and answer, and during that time, you can feel free to put your videos back on. So let's see here. I want to advance my slide. There we go. So this program is part of our community education offered by the Land Steward program. And if you are interested, you can just search OSU Land Steward program and click on the little join arrow or check mark that you'd find and find out about other upcoming classes. I'm sorry, there's a little bit of a delay. That's if I sound like I'm not speaking correctly, it's because I'm a little distracted by that. But December 15th, we have mushroom cultivation. And on January 12th, we have iNaturalist and other citizen science fun. So those are upcoming. And again, if you want to hear about them, just join our email list there. And then at the end of this presentation, we'll have a really quick, super quick poll just to find out how this is working for you. Just 3 questions. So before you sign out, please take a moment to answer those 3 questions. So we'll launch that at the very end of the program. And so with that, let's see if I can advance. I wanted to introduce our very wonderful instructor today. We love Jad D'Allura. I think you guys are really going to enjoy this. He's been giving a version of this class for us for a few years, and every time I learn something new. He also taught for us for the Oregon Master Naturalist Field Program, and we really enjoyed that. He taught at Southern Oregon University for 33 years, and in his retirement, he teaches chemistry just to keep things fun at SOU. I'm not sure if he's doing that right now, but he also does a lot of field works. He's been working in the Cascade-Siskiyou National Monument, helping to map that all out, pass on all he knows. Okay, with that, I will turn it over to Jad, and it'll take him a second to start sharing his screen. Unmute.
And start video.
Yep.
Okay.
Start video.
Start video. Okay, and share screen and grab this.
Yep.
Oh, double click. There we are.
Okay.
Okay. I think we're ready to go.
Okay.
I'll just start the program.
Yeah.
So there's a little picture of me in there, so they see that you know, I can run, but I can't hide.
Right.
Okay. So let's see. Whoops. So basically, here we are. We're taking a respite from listening to all of the political flack that's going on right now, taking a little break away from that, and going to start talking about geology, which is always interesting, certainly to me. And if we want to take a look at the geology, it's something it's kind of like opening a book, and you open it up and they're all blank pages. But the more you know, the more the writing appears on those pages. And hopefully by the time this particular demonstration or lecture or whatever this is going to be is over, you'll take something away from you, which will be primarily an interest in trying to expand your knowledge of what's out there. And you'll see that this particular book of geology ties into so many other books, botany, the animals we're dealing with, all sorts of things that are in the natural environment. And you can see those connections too. I'll mention a few as we go along, but I leave it up to you to see some connections with your field of interest and geology. So buckle up, here we go. We're going to go through about 250 million years of time, and hopefully you won't get whiplash. So we're going to talk primarily about the geology and southwest Oregon, only a portion of it that's outlined by this black box. And we're taking a look at some of the older rocks first, the Klamath Mountains, Cascade-Siskiyou Mountains, and of course the Bear Creek Valley in which most of us live. Also, some of us live in Williams and other places around, perhaps Grants Pass, or maybe even Klamath Falls. And we'll take a look at the Western and High Cascade volcanoes that flank the valley on the northeast side. Those rocks are quite different. And the reason the valley is here is going to be revealed in this particular talk. So first we'll start out with the oldest rocks and work up through geologic time to the present. So we take a look at the geology of the Klamath Mountains. And if that frightens you, it should. It's basically kind of like a Frankenstein's monster, as I mentioned. And by the way, I put a lot of text on these slides. Hopefully that doesn't distract you. It does two purposes for me. One, it jogs my failing memory. And the second thing is that if I say something and it's not quite clear, then you can take a look at the little boxes and maybe that will help. But if you take a look at the map, what you can see is where Grants Pass is, the Bear Creek Valley, Oregon-California border, and it just looks like a whole series of pieces that have been stitched together without any seeming order. But in fact, there is an order. And this particular map of the Klamath Mountains is quite detailed. But all these colors right here that we see represent rocks of different ages and different compositions that geologists call, and this is a correct spelling, terrains. Geologists never really learned how to spell well, so that is our explanation of trying to take these rock units, all that have all sorts of different features, but yet are internally coherent, and separate them into different units that we call terrains. And those terrains will be very important as we go along a little later on. So we take a look at these rocks, and they're primarily younger as you go to the west, and they represent, now the reason there's such a variety of different colors representing different rocks is their successive collisions of island arcs that amalgamated together, or accreted as we call them, and then were swept into North America and became part of the continental landmass. Just like, as I mentioned at the little box down there, like taking plaster one after the other and piling it onto North America to make the continent grow wider. So when we take a look at all those different colors, it takes a lot of geologists who are out there taking a look at these rocks in general, and then also specifically to try to figure out what's there. And it's one of these studies, or one of the comparisons I could use is maybe you know the old story of the blind man and the elephant. And the story of the blind man and the elephant basically is each blind man sees a different part of the element. And it's not until somebody with sight takes a look at the entire information that people have put together and say, hey, that's an elephant. So that's where we are now. People are putting together lots of bits and pieces of work that people have done since the 1940s all the way up to the present and come up with a fairly coherent picture of what the geology is. But it takes a lot of workers. And of course, these are three of the foremost workers that we had looking at the geology in the monument and elsewhere. So how did all these terrains become accreted or smashed into North America? Well, we have to go back a little bit and talk about subduction, which most of you, I'm sure, know something about. And that's basically what's happening out there at the Cascadia subduction zone, where we have material of the oceanic plate, which is denser than the continental material. And that material, as it interacts with the continental plate, earthquakes occur, but the denser oceanic material is actually consumed, or it goes down beneath the continental landmass. Or you can think of the continental landmass as riding over the oceanic plate, which is heavier and going down. So I use the analogy between two trains along the same track, and they're coming at one another, but one train is heavier than the other, and the other train, the lighter train, goes underneath. And that is shown in the diagram with a little red arrow. Well, what happens if an island arc or a mass like a microcontinent, say like Madagascar or Japan or something like that, actually moves in towards the continent. It has the same density as the continental material. So what happens in that instance is it gets stuck. It can't go under the continental landmass and just sticks right up against the continental landmass. And if the plate motion keeps moving, then the subduction zone actually moves out in the diagram on the lower right to the ocean part of the plate. So a new subduction zone occurs. There's actually a landmass. It's mostly underwater right now, but it's, if you could think about Alaska and see where that big arc occurs in Alaska, it goes out towards the Aleutian Islands. There's a plate that's moving into North America just below the St. Elias area, and it can't go under. So it's going to become stuck to the continental landmass too. Hopefully that makes sense. Well, if we take a look at this mass of material that's moved in towards North America, it's going to dock, just like a ship coming up to a pier, but it's not going to leave that pier. It's going to become part of the pier or the continental landmass. And that join where the alien material that's come in has collided with North America leaves a mark because the rock types are different on both sides. And we call that a suture. So that's one of the large features that's actually separating one landmass from another. And that's why these geologists who worked in the past would go over these faults or these large suture zones and said that, hey, the rocks on the other side are different ages, different compositions, and they didn't quite know what to make of that. Well, today we take a look at it and say, well, this actually represents a collision of some alien material that came into North America and has been accreted or added to the continental landmass. So this is basically where the collision occurs. And as it does, if you take a look at the diagram, it says the Klamath Mountains are sitting there. Just assume that that's a big plate that's come in to North America, and that's added onto North America. And the subduction zone has moved off to the west. A new one is starting to the west. This is where I'd ask the audience, am I making any sense? Fortunately, you don't get to respond at this particular point. So we'll just continue on.
You can give him a thumbs up.
I can give him a thumbs up. All right. Okay. If we take a look at the rocks in the Klamath Mountains, and we take a look at them very carefully, we find out that from the fossils themselves, those have an Asiatic affinity. That is, they look like fossils, plants and animals that actually existed in China and also in the other part of Asia. They have nothing in common with North America. So how did they get there? Well, you know the answer now. That particular landmass moved into North America and collided. You might ask yourself, how does this stuff move? Well, basically what it's doing is it's moving on a plate, the subducting plate. And then as that subducting plate gets closer and closer to North America, and the subducting plate can't go down anymore, that's when the collision occurs. And that's when the suture is developed. So we find a lot of fossils. We find rock types too that have similarity with rock types in Asia. So we know that this material originally oriented somewhere around the equator and has moved in towards North America. There are some arguments that actually they occurred at a lower latitude, but that's still being worked out by geologists today. The same three geologists I showed you before. So we do have in the Klamath Mountain rocks that are as old as about 560 million years old, but they're little tiny slivers. And also rocks that are older than that, about 400 to 250 million years old. They're in the mountains too. They're preserved primarily in Eastern California, but there are some also in the Klamath Mountains to the west. But most of the rocks that are in this general area, in that square that I showed you on the geologic map of Oregon, have been generated during the Mesozoic, which is about, roughly 140 to 250 million years ago. And they were accreted offshore. That is, they didn't collide into North America, they collided into one another and then moved towards North America and docked with North America after they were basically amalgamated together. So you can think about another analogy, not a really nice one, but that big island mass of plastic that's floating in the Pacific Ocean. And assume that that's a continental or a island arc landmass. And now take a look at the tsunami in Japan in 2011. That generated a whole mass more of material, plastics in general, that has moved in and has joined that big mass that's sitting out there in the Pacific Ocean. Now imagine at some future date, that stuff is swept into North America by some act of God or something. Then that may become accreted to North America. And that's basically how these pieces in the Klamath Mountains have come to be part of North America. Well, what do they look like? Here's a picture, somewhat schematic. It's just like a series of dominoes that are basically thrust over one another. And each one of those dominoes right there, you see in the diagram, represents a different terrain with different fossils, different rock types, different ages. And they are juxtaposed against one another and thrust out towards the west along large faults. So what happens when all these terrains dock with North America or one another? Well, if you're closer to the surface, there's less pressure and less temperature, so the rocks behave in a very brittle manner. That is, they break and they generate faults. So we have a whole series of faults that we have closer to the surface of the Earth. Now that surface of the Earth can go down 15 kilometers or more and still develop faults or ruptures in the surface of the Earth and generate earthquakes too. But some of the rocks are actually folded and some are extended. How does that happen? How do rocks actually fold? These are hard rocks. You pick them up, you can't fold them. So how are they folded? How do these rock types actually not break brittly, but actually are pulled apart to generate in the lower right diagram what we call, the French call, boudins, or sausages. They look like sausages. And it's a product of extension. And on the upper right diagram, there are folds. Those layers right there have been compressed like an accordion. So how does that happen? Basically, that happens at great depth where now the pressure and the temperature are increasing. Then the minerals no longer are stable. And what they tend to do, we can get into the physics and the chemistry of these particular minerals, they begin to break down because they're not stable under higher pressures and temperatures. So the individual components break down and ions migrate through the rock very slowly. So rock layers actually, you can see in the folded diagram right there, some of those materials are not folding as well as other materials. So each layer is made of a different type of composition and they behave differently. And that's why we can still see the original fabric of the rock, even though it's now changed or altered. We call this process metamorphism or a change, just like a caterpillar turning into a butterfly. But in this instance, it's not a butterfly. It's one mineral changing into another mineral and other minerals next to it changing. And as they do this, it's kind of like a marble cake, if you want to look at it that way. You can put all these layers relative to one another, and each one of those layers is a little bit different composition. It might be cake, it might be frosting, cake, frosting, and those layers are going to behave differently. When you actually compress that cake by falling and dropping it on the floor or something like that, then they tend to fold into one another. That's not the exact analogy of metamorphism, because actually what happens is those layers change their compositions. So hopefully that's a little bit explains how these rocks can actually fold or be pulled apart And that's happening during the collision of North America. It's not happening instantaneously. It's like earthquakes. Earthquakes may be instantaneous to us, but a mountain range rises not all at the same time, but in increments. It might go up 50 feet in one episode, but that's not as high as a mountain range. So it takes a lot of episodes for the mountain range to be generated. Same thing with these faults, same thing with the metamorphism. This takes a lot of time, but hey, we've got a lot of time, 250 million years. So we can do anything in 250 million years. All the rocks of the Klamath Mountains are metamorphic. So let's get back up towards the surface again. Those rocks are brittle. They're not going to fold. So what happens is they tend to break up. And if they break up, they generate what the French call, another good French term, mélange, which means mixture. And it's very, very descriptive of what we see. That's a mixture. This is a melange near Gold Beach. So if you drive up the highway through Wedderburn or places like that, you can actually see these disembodied pieces of rock that are grinding past one another as the material on the upper plate's trying to go under, but it can't. So it breaks up. And the plate's breaking up too. The oceanic plate and the continental plate. Pieces are getting broken up and mixed together and coming up kind of like watermelon seeds being spit out. Perhaps not exactly, but maybe you get the idea. I'm hungry now. Well, what do Klamath rocks look like? Well, yeah, they're scary. They look quite a bit different than a lot of other rocks. These rocks that we can see along Highway 199 are actually gray slate, which used to be marine mudstone or marine muds. And they have been compacted and hardened, metamorphosed, and they were originally horizontal or nearly so, and now they're almost vertical, giving us a good idea that these mountains have been compressed and tilted. We also can see pillow lavas. These are kind of neat things. So those people who've gone to Hawaii may have actually seen these things flow into the ocean, not too close, of course, but they actually originate. If you take a look at the diagram on the upper right, there's a crack. It's a brittle break in the Earth's surface. And of course, the magma being very liquid, magma is liquid rock, finds that crack, exploits it, comes up towards the surface. As it does that, it tends to come out into very cold water. And just like, pardon the analogy, just like my sphincter, when I jumped into the cold water Crater Lake, I tend to, yes. Any rate, what happens is the magma, instead of flowing out onto the surface, freezes right there in little blobs and cools. And then more material comes out. And at the very edge over on the far right of that diagram, a new pillow comes out, kind of like, let's see, the Rolling Stones' tongue in their pictures. This tongue of lava comes out, it cools, and we just have this thing occurring over and over. So what you see in the lower diagrams are the pillows. The lower left diagram is a cross section of the pillows, and you can see the pillow type shapes, and they got the name because they look like a bunch of pillows. You can't fluff them anymore though. And then over on the right hand side, we see pillows that are along Highway 76. So we also can find pieces of the mantle. So we're dealing with stuff that originally was down much deeper than 15 kilometers, probably on the order of 60 kilometers or something like that, or even deeper in some places, although it does vary. This is mantle material. This is material that has a lot of iron and magnesium in it. It is very hard, very dense rock originally, and it is not like granite. Granite is the stuff that's more or less distilled and comes up towards the surface, and it originates in these rocks that we call peridotite. You might see the word peridot. That comes from the mineral olivine, and the mineral olivine is found in these rocks as well. In the lower left diagram, what you see is somebody sitting on a dark rock, and that happens to be something that's called a gabbro. You'll see another diagram of it a little later on, but basically this has a different composition, and it, if it breaks down, generates a soil that is more fertile than the serpentine soil. Serpentine can form from peridotite by the addition of water and heat. And we know that those soils are not very fertile and have their own indigenous flora. Oh, which is basically what I say in that next little box there. The only thing I add in that little box is that these rocks, or most of the aquifers that we find in the Klamath Mountains, except for the very shallow ones that are along the rivers and places like that, are fracture generated. That is, if the fractures, if a rock is really fractured, water can get into there, or fractures cross at that junction, you get more water in that particular instance. And most of the aquifers in the Klamath Mountains are of the fracture type. Up there in the upper left diagram, I wrote down Condrey Mountain Dome. I'll be referring to that in the next couple of slides. And you can see the dome-like feature there. It's as if something is just like somebody is just getting up out of bed. They were lying on prone, and now that's their back coming up. So it's a dome that's occurring in the Klamath Mountains. So now we get to the molten rock. During these collisions, there quite commonly is a lot of heat generated, and the heat that's generated there or afterwards to generate volcanoes tend to produce magma, and this magma may not reach the surface. If it doesn't, and it's fairly small, it's called a pluton. You may have heard the Mount Ashland pluton. That's one of them. There's one at Grants Pass. All those little pink pieces that are sitting on this geologic map are plutons. They're very interesting. Not only do they represent magma that's coming up to the surface but never reached it, is that some of these things actually intrude or come into fault zones. And when they do that, they stitch it together. So what that means is that that fault must have been there before the pluton came in. So we can date the fault by dating the rock or the minerals in the pluton. So you take a look at the right diagram, and what you see is a magma body, a pluton, that's come in and has crossed a fault. Therefore, it's younger than the fault. So we can date the pluton, you radiometrically age date it, and we say the fault must have moved before this pluton came in. If the fault cuts the pluton, then the fault is younger. So there's the Mount Ashland pluton. It's about 163 million years old. That MA stands for millions of years ago. And here is the Grants Pass pluton, one of the youngest ones in the Klamath Mountains, at 136 million years. It's very interesting. If you take a look at the Mount Ashland pluton, that's where the ski area is. It's high. You take a look at the Grants Pass pluton, it's almost a bowl. So those rocks weather differently. There's a reason for that, but we don't have time to get into it. And there's the Condrey Mountain Dome. Okay, see, this is shaped like a little oval, isn't it? Well, the Mount Ashland pluton has been tilted. Here we get into the Condrey Mountain Dome. If this dome rises, the rocks around it are tilted away from it. Not only that, as these plates are shoved up against one another, they tend to make the Klamath Mountains rise. So as subduction occurs off of the coast of North America, that acts as sort of like a shim, a little triangular piece you put in a doorway to keep it from closing. And if you put enough shims in there, that door rises up and up. So the Klamath Mountains are rising because of that. And the Condrey Mountain Dome has also had an effect to tilt the pluton towards the east. So you can see in the diagram over on the left-hand side, that pluton, the oldest part of the pluton, is in the south in California. And the youngest part is up around Ashland and towards Talent. So if we take a look at the compositions of this pluton, when a pluton first forms, it has a lot of iron and magnesium in it. And that stuff crystallizes out in the early minerals. And that's what's shown on the very bottom part of the diagram. That's the oldest part of the pluton. That's made of gabbro. And that can break down and form a pretty fertile soil. As we get over towards the northeast, you see those different colors represent slightly different compositions in the pluton. And the youngest stuff is up there at the top, and it has almost no dark minerals in it. That's what's shown in the diagram, the picture on the right side. That is the granitic material. It's coming into cracks in the early crystallized part of the magma. If you think about it, almost every natural feature that we've got, except ice, tends to contract when it cools. So if the earlier part of the pluton is cooled down, it will crack. And if it's cracked, then the fluids, the later fluids that are left in the magma, will inject itself into those zones of weakness. That's exactly what's happened here. This is on the Mount Ashland Road. This next picture is also on the Mount Ashland Road. Now think about it. When these rocks are being thrust over one another, that's generating a lot of pressure, and the rocks tend to break up. So we'll see lots of fractures. See a little fracture there shown by the arrow? Lots of these little fractures occur in the pluton. Some of them actually are ground so fine that they are like clay and they don't allow water to pass through them. But other ones are open, and they too form conduits for water, reservoirs of water. And quite often, if you take a look at the Mount Ashland pluton, some of your taller trees are growing along big cracks like that, because they can tap down into the root system, can tap down into those fractures and get water, whereas some of the younger trees and the shrubs can't get down that deeply. So we're not quite done with the Klamath Mountains yet. There's more history. It's not dynamic. What happened about 150 to 153 million years ago is the continent stretched, at least this part of the continent in the Klamath Mountains. This is around the Illinois Valley and to the west. So what happened is the continent was trying to split. As it did this, it's like a crack that opened up. And the bottom little box that I'm going to show you, it's like a jelly donut. If you take a jelly donut that has the liquid stuff in the inside and you pull it apart, then you're extending the crust or the donut, and this jelly rises up to fill the crack. The same thing is occurring in the Josephine Valley area. So it's splitting apart, a new little ridge is forming, just like the East Pacific Rise or the Mid-Atlantic Ridge, where oceanic crust is being created. But here's a small little area, and it doesn't have enough oomph to really go for a very long time. So what happens is the pressures from the subduction zone, which is shown on the diagram as that big black line that's going underneath, puts enough pressure on this splitting part of the continental landmass in the Klamath Mountains and squishes it back on itself. As it does this, it generates a big basin. That material that's being generated at the ridge crest is called an ophiolite. And this particular one is called the Josephine ophiolite because it's in Josephine County. So how does this originate? When this crust begins to crack there, all the rocks under high pressure are very, very hot, like going down in a mine. It gets hotter and hotter and hotter. But that material doesn't melt until you actually release the pressure. Once you release the pressure by cracking the crust, then the jelly from the donut starts coming up. Boy, I really am hungry. I should have eaten more for dinner. Oh well. Well, what is an ophiolite? Well, it's analogous to the back arc basin that's opening up between China and Japan. So we see that particular back arc basin, which is the Sea of Japan in our present day analogy, and it generates a vertical cut through the crust. At the very bottom is the peridotite that we looked at earlier. That's down quite deep. And then material starts coming up to form magma bodies, and those begin to crystallize. Those are beneath the surface of the earth, and they are quite rich in iron and magnesium because they're coming up from the mantle itself. They're not coming through continental crust. They're coming through no crust whatsoever. And they're generating pluton bodies that rise up, those little lines that are sort of pointing towards the surface. Those are called dikes. And those lead to the pillow lavas on the surface of the ocean. And then on top of that, quite commonly, we get mudstone or we get other materials that lie on top of them, oceanic sediments. So that entire thing is called an ophiolite. So basically, and I mentioned this earlier, the peridotite is really pretty unstable when it gets towards the surface of the earth. And as it's coming up, it's encountering water, which is not very common down there deep in the mantle. And as it does that, then these minerals, the olivine and other minerals, begin to alter to serpentine. And that's what generates the rock we call serpentinite. And this serpentinite is not very strong. You go through road cuts, it tends to slough off. That's where along the freeway, I-5, they have some problems that are, oh gosh, where is that place? North of Hugo. So there's the gabbro, a little bit higher up, and it's less rich in iron and magnesium, has a little bit more nutrients in it. It has potassium and sodium and other minerals that plants tend to like. And then we get towards the surface, the pillow lavas have even more nutrients as they tend to break down. Okay. I guess this is where we sort of stop for a bathroom break and maybe a few questions. So we'll see how the questions occur. So what should I do here?
Okay. Put yourself on mute.
Oh, put myself on mute. How do I do that?
So we'll give you a moment for a little bio break and let that settle in. It's a lot of information. And then write in some questions to the chat, and we'll try and answer a few of those if you have any questions. Otherwise, we'll just continue with the presentation. We'll give you about 4 minutes here.
Stop the slides and just bring it back up and resume from the slide. Would that be easier?
I think you can leave it. So much.
The next day, I came back.
Get in shape for it, for sure.
Or should I take this off and go, well, let me see, I'm not quite sure. I go back to a picture of me, or should I leave it up? Because people might ask questions about the PowerPoint. You should take and go back.
Oh, yeah, okay. It's probably easier to keep it up a little bit, I think,
Okay, okay,
for that purpose.
okay. Sounds good to me.
Anybody has some questions?
You can sure tell what we do. Painting. The colors are so bold.
getting some questions.
Getting a couple questions?
You want to see it? You can actually look in the chat. You chose the bottom if you want.
I do what?
In the chat. I think we can come back on now though. So Jamie will ask you the questions.
Oh, she will? Okay.
Mhm.
Okay.
Yeah. that'll
Okay.
be easier.
Are you ready, Jad, or would you like a couple more minutes for a break?
Oh, I'm ready.
Okay, great. I'll pull up the chat and I'll be right with you.
Okay. I'll be thinking of lies, falsehoods, and deception in the meantime.
I don't believe that's probably the case. So the first question was, it seemed like it related to plutons. Are they typically made of granite?
Ah, good question. So am I back on the air? Will they be able to hear me?
Yep.
Okay. I can either go back to the picture or just espouse right here. I think I'll espouse. And if they want to take a look at a picture, I can go back to it. But basically, the plutons are of different compositions. And if we take a look at the Sierra Nevada, for example, there are so many plutons in it, it's called a batholith. We have all sorts of terminology in geology. But the important point is that these plutons can be really different composition. So for example, the ones that I just talked about in the Josephine ophiolite, those plutons are very, very rich in iron and magnesium minerals, and therefore they're quite dark. So we'll see some of those either parts of a larger pluton or just as a pluton itself, as in the case of the Josephine ophiolite. But if you take a look at the Mount Ashland pluton, it is actually a sort of a composite pluton. So when the magma comes up, there's a process that we call magmatic differentiation. And that is essentially a magma differentiating into different parts as it cools down. So you can imagine a mass of molten material coming up from the subduction zone or from a ridge crest or wherever it comes from. And as it comes up, some of the minerals begin crystallizing out early. For example, olivine crystallizes out at about 1800 degrees Celsius. And something like, some of the lighter colored minerals or some of the micas, for example, will crystallize out at about 600 or maybe 700 degrees Celsius. So different minerals begin crystallizing at different times. So as this pluton comes up, it's crystallizing out the darker minerals first. And as that occurs, it's differentiating. The rest of the magma is lighter in composition because the dark minerals are heavier. So they tend to stick around the bottom or the sides of the pluton. And as the pluton, as we take a look at the pluton as it's crystallizing, there's less mass to crystallize, and it's starting to crystallize out other minerals that crystallize at lower temperatures. So as that happens, then the pluton differentiates itself even more. And that's why in that picture I showed you of the Mount Ashland pluton, the earliest material was called gabbro, had a lot of dark minerals, and the lighter stuff was very rich in quartz, and that's the granite. And there are all different compositions between them. Not to blow you away, but we have all sorts of different names for different associations of minerals: monzonite, quartz monzonite, tonalite, quartz diorite. And these are all sorts of materials that are in the pluton, but look a little bit different because they crystallize at different times. Did that
That's really
answer your question?
fascinating. So would that mean that plutons, for instance, the Mount Ashland pluton versus the Grayback Mountain pluton, the composition may be completely different between the two because of that?
Yes, that's right. The Grayback pluton has darker minerals, a greater composition of the darker minerals as compared to the upper parts of the Mount Ashland pluton. And up around Mount Ashland itself, you can see all sorts of quartz veins and granite. They're cutting in through the darker rock that we call diorite. So yes, they can be different compositions because they came from a slightly different origin.
That's so interesting. Related to the gabbro fact that you just mentioned, someone wanted to know what makes the gabbro or soil rich. What minerals are in it?
Oh, okay. Well, the gabbro does contain a lot of iron and magnesium minerals. That's why it's a darker colored rock, but it also has a lot of mineral we call plagioclase. And the plagioclase has calcium and sodium and aluminum and lots of trace elements in it that don't really occur in the peridotite. Well, actually, that's not true. They are in the peridotite, but they're in such minute amounts that you don't really get much of it until you begin partially melting the peridotite. As you partially melt the peridotite, all of the materials that don't, that are less stable in the peridotite tend to go into that fluid. And that fluid that's coming up towards the surface, or magma, will contain more sodium and potassium and these other sorts of materials, and also phosphorus, that are in just minute amounts in the pluton. But when you melt maybe 3 to 4% of it, that 3 to 4% is much, much more enriched in materials that our plants use at the surface of the earth.
Mm-hmm. Interesting. As far as like surface of the earth, someone was wondering what causes the high levels of boron in well water. They said that they live slightly west of South Medford.
Slightly west of South Medford. Oh, um, hmm. The higher boron level is usually associated with the volcanic rocks. And the volcanic rocks, or as I'll get to a little bit later on the talk, they occur to the northeast of the valley. So we would expect more boron in rock or in wells that are to the east of the valley. As you go to the west of the valley, there's less boron in those minerals, those rocks, because they're normally not quite the same composition, and they've all been metamorphosed. Some of the boron's gone. It's pretty mobile.
Mm-hmm. Okay, and I know we're just taking a short break, so maybe I can just throw a couple more questions at you, and then you can get back to the presentation. How does
Sure,
that sound?
that's
Okay,
fine.
I'll just join them together. The first question was, where can one find that colorful geological map of the Klamath Mountains? And the second question was, around Harris Beach State Park, just north of it, are those pillow lavas along the cliffs and in the sea stacks?
Uh, where is that again?
They said around Harris Beach State Park, just north of it.
Harris
And I
Beach.
think, is that around Gold Beach or?
No,
I'm not
that
sure.
I don't know. There aren't too many there. There's a process that's called spheroidal weathering or exfoliation that tends to produce roundish shapes, and maybe that's what the person's seeing. But the pillows, the a large mass of pillows that occur are best seen around Roseburg or heading on Highway 42 near oh gosh, what is it, Bridge, and places like that. So you'll see the pillows there, very dark rocks and bulbous shapes. That's where a lot of the pillows are. And in fact, this is not part of the talk, but there is a plate that is mostly oceanic that is stuck up there in the southern part of the Willamette Valley, a little bit north of that too. And that is a piece of oceanic crust that's stuck in there. And that has a lot of pillows in it. Yeah.
Interesting.
Mhm.
Someone just corrected me and said that Harris Beach State Park is around Brookings.
Yeah, that's right.
And then so the first question was, where can one find that colorful geological map of the Klamath
Oh,
Mountains?
that is, gosh, I'm going to have to get back to you about that because I don't have the reference. It's the U.S. Geological Survey map, and I don't have that one. I forgot to bring that with me, so I don't have the reference, but I can give it to you and to Rachel, and then that can get back to the person who wrote the chat, or she can, or either one of you can put it into um, information to send out later.
Perfect. Yeah, maybe we can send that with the link for the recording. That
Okay,
sounds
okay. It'll take
great.
me a day to figure that out.
Perfect. Well, thanks, Jad. We'll get back to the rest of the questions at the end of the presentation, but for now, if you feel up to it, we can just get right back to it.
Oh, I'm up for it.
Perfect.
You know, I was a teacher. I
Yeah.
just talked all the time. In fact, it's hard to shut me up. Okay, well then we will start. So let's, whoops, I don't want to do that. There we go. So we're ready for the trip through geologic time. And now we're pretty much done with the Klamath Mountains, at least the snapshot of the Klamath Mountains. So After the Klamath Mountains were accreted to North America, there was a great period of uplift and erosion, and also a rise in sea level for reasons that we won't get into. But basically, all the continental land masses were experiencing a rise in sea level. And you can see the picture that I've just put up there. And you see the large continental sea. This is where the plesiosaurs and all the dolphin-like animals, the ichthyosaurs, those were romping around in through there. The dinosaurs were traveling all over the place. But our little place is right there. And our valley was actually inundated by water to the west of the Klamath Mountain, or pardon me, to the east of the Klamath Mountains. And as that happened, then these older rocks, the Klamath Mountains, were being eroded. And as they were eroded, the sea encroached upon them. And as it did that, it laid down sediments that were being eroded from the Klamath Mountains and also elsewhere, but primarily from the Klamath Mountains. There's some indication that there were sediments coming from the Sierra Nevada too, but primarily the Klamath Mountains. So if you see the diagram over on the right side, this shows us a little diagram of rocks that were being deposited across an earlier diagram that I showed you. And those rocks are sitting on top of the eroded rocks in a surface that we call an unconformity. It's kind of like a teenage sun, right? Anyway, so we have this material being deposited upon the Klamath Mountains in a rock unit that we recognize and call the Hornbrook Formation, named after Hornbrook, California. And it's about somewhere around 90 million years old, a little bit older in some places and younger in other places. And that's our unconformity right there. So the younger rock actually gives the age, a minimum age for the rock it overlies. So if we can date the fossils in the Hornbrook Formation, and we can do that, then we know that the rocks it sits on top of are older. So if we take a look at the seaway, this large seaway, it actually occurred to the west of the Klamath Mountains. It's shown in the green colors there in this map that I'll show you. That, in fact, I have the reference for that map. So this particular rock unit was being deposited, all oceanic type material, and we find mostly mudstone in the valley. That's basically like shale, but it doesn't have nice layers, and it's very easily eroded, which is exactly why the valley's there. Bear Creek has been able to erode through the weaker rocks, and the weaker rocks are in the Hornbrook Formation mudstone. So that's why our valley is oriented the way it is. And if you go across the border, the Colston Valley is the mirror image of the Bear Creek Valley. The very same rock types eroded to form that valley, separated by the Siskiyou Summit Fault. So we also find ledges of hard sandstones. If you drive along the freeway I-5 from between Talent and Ashland, you'll see some of that sandstone. It's harder rock. So a little diagram on the bottom left there. It sort of shows the Klamath Mountains. Let's imagine that over on the left side. And sediment is being eroded from there, rivers, streams, just runoff, sea cliff failures, things like that. And the sediment's going down into this basin. And the coarser material, the sandstone, is closer to shore, and the finer material is further away, except where there are alluvial deep sea fans, like the Astoria fan off the Columbia River, which carries a lot of sand into the Pacific Ocean. So this is a picture of the Willamette Valley right here. It's much younger than our valley, but the same sort of idea is occurring. In other words, we have a valley between hard rocks on both sides, and the rock that's being deposited there in the center is weaker rock. Hence, the rivers can carve through the valley and create that nice lush farmland. We also have fossils there near the Siskiyou Summit, which you may have seen as you get closer to the Siskiyou Summit. There's that big cement sort of barrier, If you look at the steep cliffs up there, keep your eyes on the road though, but look up at the steep cliff barriers, you'll see little white lenses that are going through the sandstone. Those are lenses of fossils that are washed off the beaches during storm surges and deposited in lower areas in the sandstone. And so you can see lots of different fossils, and those fossils give the age of the Hornbrook Formation in that area. So now we move a little bit up in time. Now the Cretaceous seas have decreased. In other words, the sea level is going down. There are glaciers and things like that trapping the water. So we have then deposits of the Payne Cliffs Formation, named after our local Payne Cliffs in this valley. And these are sediment-choked streams that are deposited during what we now call the, let's see, I think I put in the next box. No, somewhere in here. There we go. The Eocene hot box event. Some people are actually arguing that we're moving in towards another hot box situation with the global warming. It may be a little overstated, but I'll tell you what happened during the Eocene hot box. There was a lot of rainfall that occurred, and that rainfall caused a lot of erosion, and that erosion choked the streams. And as the streams moved towards the west, they just essentially denuded a good portion of the western part of North America. So really hot, a lot of rain, a lot of erosion occurring during the Eocene hot box. There's no mountain barrier to keep these streams from flowing from the east towards the west. There is no cascade range. So there's nothing to stop those streams as they're moving towards the west, choked with these sediments. And these sediments look much like what we see coming off of Alaska, which is shown in the lower left diagrams. Those are called braided streams. I think you see how they got their name, look like a whole bunch of braided hair. And these streams are very shallow. And the reason they're shallow is because they're dumping a lot of material and changing their channels. So what do we see in the Payne Cliffs Formation? Well, there's the Payne Cliffs right there. And what we see are these rock types. We see a lot of sandstones, a lot of pebbles, and the pebbles are kind of free floating. There's not big gravel deposits. There are some stream deposits there, but most of the stuff is coming down and it's just choked with sediments. So all these pebbles appear to be floating up in the sandstone. And some of you, or some people in the past have asked me, where do all these big white cobbles come from? Well, those are Precambrian in age, and they come from the continental landmass, washed off of the continental interior and carried all the way over here. Oh, I should go back. Let's see, let me go back. Oops.
With the arrow,
Hmm?
oh, with the arrow might do it. Sorry.
Oh, that's okay. Yeah, I forgot. I got derailed. Hey, that happens quite often. Well, at any rate, we see a lot of these sediments that are occurring, and where do they come from? Well, a lot of them, people have been actually investigating this material, and they find by taking a look at the minerals where the minerals came from, and they come from the Klamath Mountains, and they come from the Sierra Nevada, and they come from Idaho. So we see lots of different sources that are generating all the debris that's coming off the continental landmass and the Klamath Mountains and the Sierra Nevada, northern Sierra Nevada, to be deposited in our own little valley. So now volcanism begins. So we have the Cascadia subduction zone, which is sitting about here off the coast. And we also have the Western Cascade volcanoes, and we have the High Cascade volcanoes. You'll see the age difference right there. The Western Cascade volcanoes are very, very old. The High Cascade volcanoes are young. So when people talk about the Cascades, they primarily are referring to the stratovolcanoes that we see, Mount Hood, Shasta, McLaughlin, places like that. But there's an older, much more subdued volcanic chain that lies to the west, hence the name Western Cascades. So take a look at the little diagram that's in the upper right. That's showing you the subduction zone going down. As it does go down, it takes colder material, moves it down to below the continental crust, and it gets heated up because, again, as you go further down from the Earth's surface, it actually gets warmer and warmer and warmer. Finally, we reach a point that varies. It's about 150 kilometers down, maybe a little bit more, when melting begins to occur. And melting occurs in a large zone. So we get plutons coming up of different compositions. Hence, we get back to one of the questions that occurred during the break. Are these plutons all the same composition? The answer is no. Some of these plutons come from deeper sources, some come from shallower sources, and their compositions are different. So these little blobs of material is only melting part of the crustal material and part of the oceanic plate and part of the sediment. So this material starts coming up in these little blobs, just like a lava lamp. As they rise towards the surface, if they never reach the surface, they're plutons. If they reach the surface, they're volcanoes. So what we have there are the different volcanic structures that we're going to take a look at the Western Cascades first. So here's the same picture I showed you earlier that had the Payne Cliffs Formation and also had the Payne Cliffs Formation is kind of shown in that pink color. That's northeast of the green sandstone and mudstone of the Hornbrook Formation. But now we're taking a look at the Western Cascade volcanoes. And we're seeing that these volcanoes are really eroded. Actually, Grizzly Peak is the remnants of an old eroded volcano. And you can sort of see some of the constructional landforms, but there aren't very many where we can actually see the constructional landforms anymore. So the oldest rocks of the Western Cascades, that is, now we're starting volcanism. So volcanism is occurring, and it's occurring at the upper part of the Payne Cliffs Formation, but then it totally overrides the Payne Cliffs Formation that starts forming a volcanic chain. And now that chain is going to stop these big streams coming towards the west, or most of them anyway. So the picture on the left-hand side shows you, this is in the Colston Valley, it shows you the easily eroded Hornbrook mudstone forming the flatter areas, and then the ridges that are made up of welded tuffs. I need to explain that. Welded tuffs and harder rock than the Hornbrook mudstone. So over on the right-hand side is the Siskiyou Summit. That white layer is a partially welded tuff. Now, what do I mean by that? Tuff is a word we use for consolidated volcanic ash, TUFF. And that's what we're seeing in that white layer. There are actually two of them up there in the Siskiyou Summit. One of them contains carbonized and partially silicified wood. Tree trunks that are flattened, blown down, and they're flattened into oval shapes from the pressure. Those welded tuffs were ejected out of very violent volcanoes, and that's what characterizes the Colston Valley. Mostly ash flow tuffs and things like that. Airfall material coming down like you see at St. Helens, but when St. Helens blew, the north side, it produced incandescent clouds. A lot of the volcanoes in the Philippines produce these incandescent clouds that are so heavy that they don't go up in the air very far before they collapse under their own weight and rush down the slopes. 200 miles an hour, generate lightning, and so hot that when they come to rest, they actually weld back together and generated an obsidian. Those things are called welded tuffs, and those are hard. So on the left-hand side, Colston Valley Ridge, where it's quite remarkable up there, those are welded tuffs that are forming the ridge tops. So soils derived from the Colston Formation, or most volcanic ash, are very sticky when they're wet. So if you take a look at the clays that are on the west side of the valley, they're sticky, but not real sticky. In other words, if you walk through them after about 4 or 5 feet, you can kick off the mud and you're okay. But on the other side of the valley, it's especially after a soaking rain, you tend to walk a little bit higher. You know, I'm only 5'8", so I get to almost 6 feet periodically when I'm walking out there on this stuff. So we get these very sticky, wet clays, and those occur and cause construction problems that are occurring near the bottom part of Roxy Ann Peak, where there's a lot of sticky clay. So that stuff tends to move downhill. It's not very strong, and it's called shrink swell because it swells when it's wet, gets sticky, and when it gets dry, it forms a lot of cracks. So we find those on the west side of the valley, or I should say northwest side of the valley primarily, and in the Colston Valley. So Roxy Formation. There's a gradual change from the very violent volcanic character of the Colston Formation. And we see Colston Formation up in the northern part of the valley, White City area, places like that. And the Roxy Formation now begins a whole series of volcanic lava flows and debris flows and lava flows and debris flows, and it's pretty monotonous. They're probably building what are called shield volcanoes, and I'll define shield volcanoes a little later on. So a lot of these things, you can't find the landforms anymore. I've been mapping in the monument for years, and it's really hard to find an old volcanic source. Well, the deep erosion generates steep and rugged terrain. And that's what you see along Dead Indian Memorial Highway or Highway 66 when you're driving up through these real steep canyons. And then you get to the top. You know, you get up towards the Green Springs Inn, and all of a sudden the topography gets a little flatter. You're into the high Cascade rocks there, and they're not as deeply eroded. So what do some of the rocks look like? This is along old Highway 99. Just pretty close to the California border, still in Oregon. Bunch of lava flows. And those red things are called paleosols, or old soils between the lava flows. And we also see a lot of volcanic debris flows. So the volcanoes were really pretty violent. They weren't producing too much ash, but they were producing a lot of mud flows. So it must have been pretty wet back in that time too, where a lot of debris was coming down the slopes and forming these large overlapping volcanic debris flows, which you can see in the lower left diagram. That's my pack sitting out there, for those who wondered. Of course, you see Pilot Rock in the upper diagram. Then there are dikes. The dike that you see in the middle diagram is right there at the Siskiyou summit. And the dikes are later because they cross-cut that white tufaceous rock. And dikes are nothing more than cracks in the surface of the earth that have been filled by lava that's come up into those cracks and congealed. And that lava is harder than the rock around them, which is why they sit up like sails on a ship or like a sailfish. Wasson Formation, we get up a little bit higher. This gets up around Shale City Road, places like that. And there's a caldera complex like Crater Lake. And if you get all the way up there, north of the Shale City Road, you can actually get to an overlook and see the big bowl basin of that caldera. But now we're seeing a return to violent volcanic activity again. Lots of ash flow tuffs, lots of welded tuffs, lots of airfall tuffs, intermingled with lavas from the shield volcanoes. They're just sort of a mixture of everything. It's a real hodgepodge. Driving me crazy. At any rate, you can see some welded tuff right there along Highway 66 as you're going up there before you get to the Little Keene Creek Reservoir. And on top of that, the youngest stuff here is the Hepsi Formation. Now again, we define these formations because internally they have a consistency within themselves. That's how we define these formations. So these are the youngest rocks of the Western Cascades. There are younger ones, but they're buried under the higher Cascade rocks. So we see these rocks have a lot of broken lava flows and layered what are called hyperconcentrated flood flow deposits. You'll love that, kind of rolls off the tongue. There's just lots of debris that comes down, kind of like braided streams in a way. And we also see a lot of volcanic debris flow. This is kind of around Pinehurst Inn along Highway 66. So there are lots of tufaceous rocks here, and there's a lot of little landslides that occur. And this caused a lot of problems for the 1846 Applegate group as they came across. They had to actually take their wagons apart and go down across some of the ledges that were in the High Cascades rocks where they met the Western Cascade rocks. Ooh. So now we get into the High Cascades, and we have Shasta, which we call a stratovolcano. These are the ones that are majestic and draw our eyes. These are ones that are made up of lots of different compositions, and the lavas are pastier, so they form a steeper type of a volcano. And that's in contrast to the whaleback, which is real close to Shasta, which is a much lower profile volcano. And it was called a shield volcano because it looked like a shield that the Greeks would use if they just laid it on the ground. So it's made up of lava that is a lot more fluid and not as rich in iron, not as rich in silica, more enriched in iron and magnesium. Therefore, the lava is more fluid and it makes a lower profile. There are many more shield volcanoes than there are stratovolcanoes in the Cascades, and they overlap one another. Parker Mountain, Little Chinkapin, all sorts of these mountains are shield volcanoes. There's Chinkapin. Speaking of Chinkapin, you see the volcano there, and the bands that are going across there are Western Cascade rocks, which don't tend to produce as rich a soil as the High Cascades in general. And what you see, it kind of looks like the lavas of Chinkapin Mountain just sort of flowed like an ice cream sundae right across some of the Western Cascade rocks there. And of course, we get to Crater Lake. Most of the volcanoes that are active or remain active are only active for about 1 million years or a little more. Some of the extinct High Cascade volcanoes are about 7 million years old. And there's one about 9 million years old, but we're not quite sure whether it's Western or High. And before our department was eliminated, we were doing some research there at Crater Lake on the Phantom Ship. And we got an age date of about 1 million years old for the Phantom Ship, which is the oldest age date in that caldera. And of course, there's one of the investigators, one of my students. And of course, those people who've gone to Crater Lake know that there actually, if you were to drain the lake, which of course we won't do, there are lots of volcanic structures that occurred after the caldera collapse. The same thing is true in the Shale City area. There's a lot of post-volcanic eruption that occurred there after the caldera collapsed. Not too much to go. This is okay. Close to us, of course, we have the Table Rocks. The Table Rocks are 7 million years old. And there's very little of them left, but there's enough of them left to actually trace them all the way up to Lost Creek Reservoir to find the source. We can't quite find the source. It's under Olson Mountain, but we know it came from lavas that came from Olson Mountain. So we can take a look there at the nice flat Table Rocks, upper and lower Table Rocks, and those little stripes you see below Taylor rocks, that's actually the Colston Formation. Bunch of sandstone and tuffs. And I should point out, while I'm talking about it, I mentioned before that the geology books and the biology books, botany, things like that, really have a cross connection. You can see those bands there, and those bands are defined by vegetation. And those vegetation bands depend upon the soils. And the soils depend upon the rocks that are beneath them. So I can use a lot of plant life to basically tell me where faults are, because I see a lot of springs along them and taller trees. I can take a look at rocks that have less vegetation on them, mostly grasses and shrubs. And those are going to be on very clay-rich soils that don't actually keep a nice reservoir of moisture in our Mediterranean climate. So there's lots of connections between the geology and the botany especially. Well, my diagram over on the right-hand side gets to something we call inverted topography, and that's exactly what we have. at the table rocks. So take a look at the upper part of that right diagram. You see a lava flow coming from Olson Mountain, let's call it, down through the Rogue River, filling up the river. So where does the water go? It goes on either side. When it does that, it erodes the softer rock on either side, leaving high and dry remnants of the old lava flow. So now what we have is inverted topography. What was once low is now high due to the erosion of the softer rocks around it. So let's take a look at columnar joints. I'm always asked this question, how do those things form? I mentioned earlier, rocks, when they cool, crack. And what we see are columnar joints there at Pilot Rock. How do they form? Well, when things tend to, mud cracks will do this too. When mud cracks occur, that's because the mud is drying out and it's shrinking, and it generates cracks. So this is generating pressure from all those little points right in the center of those little circles or octagons or hexagons. They're cooling from the center and they generate tension. And that tension then, if you take a piece of silly putty and pull it apart, that break occurs exactly perpendicular to the tension that you're exerting. And that's what's happening right here. So we have then a lot of little columnar joints forming as the lava cools. On the right-hand diagram, you see the columns, because you're looking on the sides of that particular, let's say, table rock. But if you walk along the top, you're looking down on the top of those cracks. And those are the hexagonal sorts of features you see at the top. So that's how they form. It's pretty cool. I guess that was a pun. Okay, so erosion on both sides of the valley contributes to sediment that fills up our valley and produces the nice farmlands that we see out in this area. So we actually have abandoned terraces that you can see, primarily in Ashland. The railroad has used one of those terraces, and it's just modified it a little bit, and it drives right along one of those terraces. How those terraces are, how are they generated? Well, as the area is uplifted, the river cuts down and it leaves its old riverbed or its floodplain high and dry. So we see those particular terraces, there are 4 of them in Ashland. You can see them actually cut, you can walk up or go down Water Street or Oak Street, and you can actually see the little rises there that still haven't been modified terribly by mankind. You can actually see those old terraces of Bear Creek. Now you don't see any on the other side. So those terraces have been eroded. So a lot of the soils are pretty mature. A lot of the material is being derived off the northeast side of the valley. You have the rich, sticky clays and derived from the Mount Ashland Pluton, which are shown in sort of that magenta color or reddish color. On the south side of the valley generates our decomposed granite, which doesn't retain water real well, but it retains a lot of water within the spaces. So a lot of people use that for well-drained soil. Whatever your plants grow in a well-drained soil, use decomposed granite. So a lot of these different soils come from different rock types. No time to get into that in any detail. Here's a picture. Those pictures on the right-hand side are right before the what was it? Oh gosh, the retirement community was built right near the freeway. As they were cutting down, I was able to get in there between the bulldozers and take a look at the Hornbrook sandstone and the terrace deposits that are right on the top. So you can actually see some of the terrace deposits there. You can't see them today, but I was able to see them then. The area's been tilted. So as I mentioned before, the area is being tilted off towards the northeast because of the rise, basically, of the Klamath Mountains and the sinking of the crust in the Basin Range. We'll get to the Basin Range near Klamath Falls a little later. But the picture that's on the left side shows you really distinctive tilting of the lavas of the Western Cascades. You can see that tilting quite nicely. That's close to the airport. If you were to park there and look at the tilt, it's very obvious. And notice those big bands that are forming there. Look at the vegetation on the bands. The vegetation there is occurring on hard rock. That's where the oaks are primarily. So this is a cross section, which is a vertical slice in the crust of the earth. And then geologists project from surface features what likely occurs beneath. And what you can see there, and especially in the lower part of the diagram, is the tilt of the Western Cascades here, off to the, that's sort of in the purple, and the greens are the Hornbrook Formation that's tilted. There's more tilting closer to the valley and less tilting as you go further east because those rocks are younger and they haven't been tilted as much. Oh, there's Roxanne. And this tilting has been going on since at least 60 million years, for at least about 60 million years. And Pilot Rock, which I had age dated at 25 million years, is tilted 20 degrees to the northeast. So it's been tilted 20 degrees since it formed. So I mentioned we get to Klamath Falls, and here we are. There, the crust is actually starting to spread. It's kind of a large example of the Josephine ophiolite, which is spreading the crust. But here, it's a more massive system because there's a subduction or a subducted oceanic ridge that's underneath the basin of range, and it's still hot. It's tending to thin the crust, and it pulls apart. As it pulls apart, it tends to fracture. If you take a look at the upper left diagram, it shows you sort of fractures, curved fractures. And the analogy would be more or less taking a loaf of bread, and it's not sliced, and then pulling it apart. And you'd get all these fractures in the bread crust all the way down through the bread, which are the faults. And in the lower diagrams, that is actually an exposed fault plane right there at Klamath Falls. So, and you can see the backward tilted sort of features in the Klamath Falls area. Each one of those ridges is a decoupled fault heading down towards Klamath Lake. Okay. But that's not the whole story. The opening of the basin and range is actually greater in the south area near Las Vegas as compared to Oregon. So it's kind of like on a pivot. And what's happened as the basin and range opens up, what used to be close to the Sierra Nevada is not close to the Sierra Nevada now. It's further off into Idaho. So what's happened are the Klamath Mountains and the Blue Mountains terrain used to be closer together, and now they're splitting apart and they're further on, further to the west. The diagram on the right-hand side, I'll actually refer to it or a similar diagram on the next slide. So actually, we were part of Idaho for a while. Now, plates on the Earth are going to continue to move. The Cascadia subduction zone is still going to be a site of underthrusting of oceanic material for a long period of time, but something else is happening too. And that is shown in this diagram. We have then the San Andreas Fault and lots of other faults that are up along the Fairweather Fault up in Alaska, and lots of other faults there. And they're tending to move the crust on the lower left side further to the north. And what the diagram shows you there on the right-hand side is today, 30 million years from now, and 60 million years from now. Baja California will be docked in Alaska. So pieces are sliding, again, just sort of like like cards, a whole series of cards you put together, and you put your hand on both sides of the deck, and then you move your hands apart, slide them apart, and those cards slide too. That's essentially what's happening here on the west coast of North America. I can go back then to, oops, where's my little, there we go. Go back to, ooh, one more. This other slide, this little piece right down in here's the Franciscan. The Klamath Mountains are sort of north of where it says Franciscan. That's actually the browner stuff right there, the Klamath Mountains, are getting close to the Klamath Mountains, and they're part of Wrangellia. And you see other pieces that have slid up here that are part of the island arcs that were amalgamated and came into North America. and then they were cut up by faults that are sliding towards Alaska. Pretty interesting. Whoops. Picture. There we go. So, wave to Baja as it moves by. So, thanks for your attentiveness. That's one of my students right there. Yeah, I think I was lecturing at the time. I'm not sure. And time for questions. But before I take questions, I'm going to put up some little references. There really is no general text for the geology in the Rogue Valley. I've been encouraged to write it, but I'm still doing research with U of O students, so I haven't had time. But there is a detailed map. I actually had pictures of it in this talk, and it's free, but it's very geologic-ese. In other words, it's written for geologists. You can probably get a few nuggets, another pun, out of it. And you can go, it's free. You can go to the open file report in the Oregon Department of Geology and Mineral Industries. You can Google it, and you can dig down or mine down through it, and you can get it. It's a pretty big report, and I have a copy of it here. And also, if you're just interested in geology of Oregon, written with some geologic background, but written in a beautifully illustrated way. And she's very, very articulate. Marley Miller, U of O professor, has a Roadside Geology of Oregon, the second edition. First edition is not as good. Second edition was by Marley, and it's much, much better. So you can take a look at those. And then I'll try to find the reference for that geologic map of the Klamath Mountains and give it to Rachel. So
That was fabulous, Jad. Thank you so much.
You're welcome.
You did a wonderful job, and I thought I learned a lot from you during the Master Naturalist course, and I feel like I could just watch this presentation over and over and just hope to retain a little bit more each time, because I find it just endlessly fascinating.
Well, I find the same thing when I'm out there in the field. I'm looking at rocks, and after a while, I say, I want to look at something else. So I'll take a look at the flowers and take a look at some of the insects and things like that, and learn a little bit more. And I've learned a lot about not necessarily the scientific names of the plants, but kind of where they grow and why they grow there in a very general way.
And associations. It is really great. You feel like you get a bigger picture too the more you learn about all the different seemingly disparate aspects of the natural history, but putting them all together just gives such a richer story. So I really appreciate you being able to do this presentation for us today. It looks like everyone has really loved the presentation too. There's a really rich dialogue in the chat. Are you ready for some of the questions?
Sure.
It looks like one person wondered, they said that there's a large, they were under the impression that there's a large ocean-sized body of water far beneath North America. Is that true?
No.
Okay.
There definitely are places, for example, back east in Florida and also in certain parts of Kentucky where there's a lot of limestone. And those limestone chambers themselves can be hollow and will retain water. One of the problems that Florida is now facing is that a lot of water that is in those underground aquifers that are in those bodies of water are being tainted by seawater because they're pulling out the fresh water too fast. So that's the only place that I know of where there are large reservoirs of water. And they're primarily in limestone and in areas that are fairly moist. Get a lot of rainfall.
Okay. Someone asked, how does the granite end up as mountains if they're formed buried?
That's a good question. Well, basically, what we're taking a look at, I'll just take the Mount Ashland Pluton as an example. There are various estimates of how deep that material was as it crystallized. And you have to think about it a little bit. When that magma is coming up, rock is a good insulator. So the rock around it is actually retaining the heat inside. And that's why the crystals in the Mount Ashland Pluton are so large as compared to lava flows that we'll see across the valley in the lava flows. So that's just sort of a background bit of information. But if you take a look at the plutons as they come up, they crystallize, most of them crystallize at great depths. Now it varies with respect to the plutons. There's one that occurs up, oh gosh, what volcano is it? I think it's, I think it's Hood, but I could be wrong. One of the volcanoes in Washington, where the pluton came up so close to the surface that it actually erupted into an ash flow. But that's really atypical. Most of these things cool at temperatures about 6 kilometers, I mean, pressures about, depths about 6 to sometimes as deep as 15 kilometers down. So let's take one that's somewhere on the order of, say, 7 or 8 kilometers down. That means essentially what you have to do is erode 7 or 8 kilometers of material. And that's what's happened on the Mount Ashland Pluton. It's actually a little bit more than that, about 11 kilometers. So those Klamath Mountains have been rising through time as subduction occurs. And as a result of that, sediment is being washed into ancestral Bear Creek and down the ancestral Rogue River and deposited offshore. There's a lot of material that's moving off the continental landmass and being deposited in the oceans. So think about that. That actually is mind-boggling. But if the Mount Ashland Pluton is 163 million years old, that's 163 million years of time of uplift and erosion to get down to the level of where the Pluton crystallized.
Mm-hmm. Wow, that's so interesting. You can really see history that way when you look at it from a geological point of view.
Oh yeah, geologic time is something that we deal with on an everyday basis, or as most people think about it in terms of a lifetime or something like that. We have to think in much, much, much greater detail in a time span.
Someone wanted to know if all rocks in the Klamath are metamorphic. Doesn't this imply that all the rocks in the island arc were metamorphic before the collision? Because the rocks towards the, quote, top of the island arc mass don't get subducted enough to metamorphose.
That is a good question. And the answer to that particular question is somewhat analogous to what I just mentioned with respect to the erosion of the material off the Mount Ashland Pluton. So what we're dealing with in the amalgamated, let's call a little microcontinent, a whole series of island arcs that moved into North America and collided about 145 million years ago. That stuff right there has been eroded, uplifted and eroded for at least 145 million years. So we're dealing with, again, a great period of time for uplift and erosion. And now the volcanoes that may have existed on those island arcs have been long eroded. And their sediments are spewed all over the Pacific Ocean. So that material too has been eroded over a long period of time. The Klamath Mountains have been coming up for a long period of time, not consistently at the same rate, but they've been coming up for a long period of time. So what we're seeing is actually the deeper roots of those old island arcs.
Interesting. For as new and young as Oregon is, because if the coast used to be in the coast of Idaho, it is interesting to watch that sort of history play out. We can actually still see some of those remnants of that taking place here. You go out in the Ashland area. Remember, you showed us with the Master Naturalist course, actually seeing some of those cliffs. You could see some of the evidence of that all happening. You could see even shells in the place of some of those cliff sides, and it's really a fascinating place to live for that. It's really great. Someone wanted to know, is it possible that there could be organisms that were brought with the island arcs?
Oh, yes. The answer to that is yes. We're seeing some of the material, well, what is it? The dawn redwoods too, that are indigenous to China. The dawn redwoods are actually trees that they're not really evergreens, but they're pines. I think they're pines. I'm not quite sure what they are. Metasequoia, yeah, they're basically the metasequoia, the dawn redwoods. So they're actually shed their leaves in the winter, and then in the spring they come back. So they look dead in the winter, but then they come back. Now that's related to Chinese, some of the Asiatic flora, and there are other ones too.
But they're fossil.
Yeah, there are a lot of fossil materials that we see that were brought in. We can see a lot of the metasequoia needles actually in the Colston Formation. So they were within the Colston Formation. They had become part and parcel of North America at the time.
This question is a little bit related. Someone wondered, are there land masses in the Pacific moving in our direction now?
That that's a hard question to answer because we're going to be dealing with a long period of time there. There are pieces of in the Philippines islands that are actually moving towards North America. There's one other one that in the Marianas Islands, which are sort of south of Japan, there's a big arc there. There's the Pacific plate is going underneath the Marianas Islands, and the subduction is occurring under those things to the west. So that particular part of the Pacific plate is disappearing, and the Marianas Islands is moving towards North America. It's got a long way to go. But the answer would be yes, there is something that's moving towards North America from the Pacific Ocean basin, but it's going to take quite a while to get here, if it does.
Certainly not in our lifetimes, but yeah.
No, I don't think so.
Yeah.
I don't intend to live quite that long. Unless my intelligence put in Android.
Someone was wondering, they said, I've seen pictures of hexagonal basalt pillars and was told they're formed by lava hardening. How can lava, a liquid, solidify into such perfectly shaped hexagonal pillars?
Okay. Well, basically, let's see if I can get back to that slide. Where am I going to go here? Doop. There we are. Okay, there's the picture. Okay, so the diagram that's shown on the left-hand side, lower left-hand side, is showing our magma, which is kind of a yellowish color there. And the magma, as its form, of course, is liquid, but like all liquids, except for ice or water, when it tends to freeze, it contracts. That is, it loses volume. And if it loses volume and cracks, then it's going to form these features, which are hexagonal, ideally hexagonal sorts of shapes. So let's take the diagram on the lower right side where it has the 120-degree angles. And that's really idealistic, but it occurs. And what's happening, if we take a look at the lower of the diagrams, or the lower hexagon, and then go directly north of it, go right into the center of both of those. That's where crystallization is occurring. Crystallization is occurring at certain nodes all the way through this lava. And it's occurring in these two different nodes. And what it's doing as the lava cools, it has to contract. It has to lose volume. So what's happening is I use the analogy of silly putty. Almost everybody's played with silly putty. And if you have the silly putty and you pull it real hard in two different directions, then that's your tensional forces. And those tensional forces are going to make a fracture exactly perpendicular to those tensional forces. So our nucleating centers are the pulls. Those are the pulling that's going to break a fracture right there, exactly perpendicular to those two cooling centers. Now put a third one in, where the other 120-degree angle is. That's cooling too, and it's generating a tension. And it creates a fracture. And then that fracture creates other fractures as the cooling center occurs through this lava in a relatively homogeneous manner. Because the lava, if it's really fine grained, it's going to be really homogeneous. And it's going to start cooling from the top down. And where the top is, especially if it's a flat lava flow, it's going to generate a feature that is not only homogeneous, but will generate beautiful hexagonal shapes. If you take a look at the hexagonal, or at the fractures, excuse me, the columnar joints of table rocks, you'll find most of those are not 120-degree angles. And the reason for that is it wasn't as homogeneous as the Devil's Postpile from which these diagrams were taken. There you had other crystals that were already formed in the magma. And that generates something that's no longer homogeneous. But still it cools from those cooling centers. It just generates a little different shape. So sometimes those angles are not 120 degrees. Did I totally snow you?
That was such a fabulous answer. Thank you. I think that's great, especially with the visual. Someone else would like to know, would the lava flows at the Craters of the Moon National Park in Idaho be considered a pluton, or is that different?
No, that's not a pluton because the plutons cool beneath the surface of the Earth. They're going to have larger crystals because they cool slowly, and the crystals then conform to a larger size. But a lava flow, when it comes to the surface, doesn't cool slowly. It cools so rapidly that there are so many nucleating centers that every crystal actually goes to impinges on the next crystal and then can't grow anymore. So the lavas are really fine grained. So that's lava that's come to the surface of the Earth and cooled really, really rapidly, and probably doesn't have very many crystals in it. The crystals that are in there probably formed before the lava was extruded to the surface.
Mm-hmm. We have another Pluton question. What terrain did the Ashlon Pluton intrude?
It's called the names have changed a little bit, but it's called the Western, well, it was originally called the Western Paleozoic and Triassic Belt, and now it's called the Hayfork terrain.
It's nice that you have an encyclopedic knowledge of that. We can just throw out trivia questions. You know the answers.
I just made that up. So
It's wonderful. Someone would like to know, with all the volcanic activity around, why do we not see more basalt?
we actually do see quite a bit of basalt. I think the youngest stuff that I'm working in right now near the Klamath and Jackson County borders is about 1.3 million years old, and that's at Chinkapin Mountain. That's a little bit further to the west near Hyatt Reservoir. But most of the rocks there, oh no, there is another one. It's about 0.33 or 330,000 years old. And that's a big basalt field. But there's nothing that's younger than that I know of in our area. So it appears that a lot of the volcanism that created the shield volcanoes has been not shut off, but it's not as active as what we're seeing in the high cascade volcanoes, such as Mount St. Helens or some of the other more active volcanoes. So there hasn't been any other ones that, to my knowledge, that have been erupting in the Pleistocene.
Someone actually, it may relate or not, but someone wondered, is there any chance that the Newberry supervolcano becomes active?
Oh boy, that's a leading question. Now that would take somebody who has a lot more knowledge than me and working in that area to answer. So I'm afraid I'm not going to be able to answer that particular one. The Newberry crater, there seems to be intermittent activity that occurs here and there and doesn't lead to anything. Like in the Sisters area, what was it, 10 to 12 years ago, there's a whole swarm of earthquakes and people were wondering if there was going to be an eruption in the Sisters area. I think it was more than 11 years ago. But it turns out that the earthquake just died away. Probably what was going on is a dike intrusion. In other words, there probably was a magma body that had found a series of fractures and was coming up into those fractures and generating the earthquakes that came up, never reached the surface. Like that picture I showed you at the Siskiyou summit of that one dike that was cutting through the older rocks. It could have been something like that. So that dike intrusions occur quite commonly and don't necessarily lead to an eruption at the surface. Now, we also had some earthquakes that were occurring on Shasta in 1987, and they stopped. I think they were called the military pass earthquakes.
And then one person had a question sort of referring back to the squashed trees you referenced earlier in your presentation. They said, were the squashed trees a tropical species or more closely related to a temperate species? They said, I'm wondering what the climate was like at that time.
It was temperate. at that particular time. That was about, let's see, that was about 20, no, wait a minute, older than that. But the climate was actually changing from tropical to temperate, but it was temperate in that area.
Mm-hmm.
Yeah, there's actually a nice display at the Roxanne Museum there in Central Point that has some petrified wood. It was done by one of my colleagues, and oh gosh, I can't remember his name, but they took a look at a lot of trees all the way from the base of the volcanic sequence all the way up to as far high as they could go. And they found that there was a change between tropical that was occurring in the Eocene time, and then about 60 million years ago, and then up towards, I think it was about 19 million years, where they were definitely temperate, with many trees like we see today.
Mm-hmm. That's interesting. Um, Someone wondered, since the Klamath area is a spreading center, are those faults transverse faults?
Most of those faults there are pretty inactive. The faults that are more active are like the San Andreas system, and they tend to be more active further out towards the coast in what we call Franciscan Formation, and further up near Gold Beach and places like that. So
Mm-hmm.
those pieces, the Klamath Mountains, a good portion of them have already slid to the north. A big chunk of them slid to the north. So
Mm-hmm.
the faults that occur there appear to be pretty inactive. There may be some little earth tremors. You know, the earth is all broken up near the surface, but there is nothing that seems to be sliding towards the north. Now, if we go further over into the Cascade Range, the Western Cascade Range, a lot of my work over there has demonstrated that there are some right lateral fault motions there. And some people who work further north of me have also discovered right lateral motion, like the San Andreas fault system. So the Klamath Mountains appear to be a block that's fairly inert, but to the west and to the east, there appears to be pieces that are sliding.
Oh, interesting. You have a lot of thank yous, so I just want to let you know that before I move on to the next question. We have about 4 or 5 more questions. Do you have the energy for that, Jad?
Sure, if you have the time.
Yeah, absolutely. I mean, I think it's everyone participating in this is just so appreciative of your expertise on the subject. So this one person said, okay, so this is a little bit off topic, but what will happen when the Juan de Fuca plate slips, and how will the Bear Creek Valley be affected? Also, are you familiar with the geologist Johan Varakamp? I've helped him get core samples a few times and think you guys would get along nicely.
Oh, I'm afraid I don't know that person. There are quite a few of us in the community here, um, up and down the coast, that I've met, but I certainly haven't met everybody. And a lot of the people that I have had contact with have retired or died, or something's happened to them. They're just, or maybe it's me. I'm not keeping up on my correspondence. But now the question was something about what would happen to the Bear Creek if and the Juan de Fuca plate.
What will happen when the Juan de Fuca plate slips, and how will the Bear Creek Valley be affected?
Oh, the Bear Creek Valley won't be all that affected, um, because it's so far inland that and it's draining quite a large area to the west and also to the east, that it reaches the Rogue River, which has been there for a long period of time, taking the waters off the higher portions of the continent and directing it towards the coast. That shouldn't change. The maybe where the mouth of the river is might change, but I don't think much is going to happen to the Bear Creek Valley, other than it's just going to continue to erode deeper, and the mountains are going to get probably a little higher.
And you might experience a earthquake, right? But it wouldn't be
Oh
very.
yeah, oh
Yeah.
yeah, there'll be definitely earthquakes.
Mm-hmm.
The big worry, of course, is the Cascadia subduction zone.
Mm-hmm.
It's awfully hard to actually calculate when that's going to go in terms of statistics, and statistics can be used to support any point of view. But essentially, we're overdue for a big earthquake. But what does that mean? Because there's a big span between earthquake occurrences. It's not like English trains. In other words, you can't tell exactly when it's going to be there. And
Mm-hmm.
same thing for the earthquake of the subduction zone. The Bear
Mhm.
Creek Valley, if there is a big subduction or earthquake, we're going to feel it here. And the
Yeah.
people in the valley are going to shake a heck of a lot more than the people on the sides that are on bedrock.
Yeah. And of course, we're not going to deal with the tsunamis. Of course, we're far enough inland
No,
that you'll
no.
still deal with the, yeah, you'll still with
The shaking and landslides and things like
Yeah.
that.
Someone would like to know, do you know if the Applegate Valley also has abandoned terraces? And they
Yes.
said, so is Applegate mostly these newer sedimentary rocks sitting on top of the older accreted material?
Yeah, in the Applegate Valley, all of the sediment that's sitting in the bottom has been eroded from all the metamorphic rock. So that could be mapped out as newer material, certainly. So when I said all the rocks in the Klamath Mountains are metamorphic, I was referring to the bedrock itself, but not all the material that's occurring in the stream valleys, in Applegate Reservoir area or places like that. And yes, there are terraces, but they're not really well developed. There are a few along the Applegate River that you can see and deal with. That's where a lot of people are farming at this particular point. There are a couple of them, but most of them they're pretty subtle. The uplift in that particular area doesn't seem to be quite as intense as it is further out in our valley, for example. But our creeks are a little bit wider. Bear Creek is a bit bigger creek.
Mm-hmm.
And the sediment is quite different. Like I
Mm-hmm.
mentioned, the mudstone erodes quite readily, whereas the bedrock in the Klamath Mountains is much harder and harder to erode through.
Mm-hmm. Okay, perfect. And then we just have one more question, and I'd like to invite anyone who's still participating, if you have the chance, we'd really appreciate you participating with our Q&A at the end of the recording. But so Jad, here's our last question, and I think it's a great one because it's kind of an overarching, and I know it's like the answer could be really long and big, but you'd be the perfect person to be able to distill it, I would imagine. What is the relationship of the Klamath Mountain Range to the Siskiyou Mountain Range?
Wow. That's that's a good question. You always hear somebody say, that's a good question when they don't know the answer. So I've said that a few times. But at any point, this goes way back to 1973 when a good friend of mine and one of my major professors and I were working on rocks in the Sierra Nevada. That's where I did my PhD. And then also she was working in the Klamath Mountains, and we saw tremendous similarities between the rock types. At that time, we had an abstract in a small paper that basically said they were part of the same basic mountain range. There are still people on both sides that are saying that, and there are other people who are saying, no, they're enough different. So I can't give a definitive answer because the argument is still ongoing. If I go back to 1973, I support what I thought then, but there's been a lot more work since then. So our idea was that basically it was splitting and that they originally were together, just as the Blue Mountains were part of the Klamath Mountains too. And we don't have enough evidence. The geophysicists haven't modeled down below the surface of the volcanic rocks very well. They've done some really good work, but they can't quite see through those harder rocks to get a definitive answer. So that's my short answer.
That's the perfect answer. Thank you so much. It was only what, 500 million years that you're expected to distill in 3 sentences?
Yeah, it's only about, yeah, that's, well, yeah, sure. There are bits and pieces of 530 million year old rocks that are the little sliver that actually the woman that I worked with in 1973, she found them in, where is it? It's down in the Scott Valley area, south of Scott Valley area, but just a little sliver of Precambrian rocks. So we know they're little pieces. We don't know where that came from. We really don't know. So there's still a lot of answers out there, a lot of answers, and more questions than answers.
I'm sure. And that's part of what's really great about being um, into science, like those things that are your information hound, and those things are changing all the time. And um, we really appreciate having folks like you in our community who have an expertise to share with all of us. And thank you everyone who participated tonight. If you have the chance to stay on and give us some feedback and answer this poll that you might see on your screen now, we'd really appreciate it. And Jad, on behalf of everyone who participated, and Rachel and I in the Land Steward program, thank you so very much.
Oh, you're absolutely welcome. I enjoy it. I can't wait till we get back to a real crowd of people and I can actually put some rocks out and people can put their hands on them and make all kinds of mistakes and yeah, and field trips too. I really enjoy those field trips. So
We did get some
hopefully
feedback
within a
that
year.
some people said that as soon as everything goes back to the pre-COVID normal, they would love to participate in a similar class to this with you, where they could actually go out into the field with you. So I think the interest is absolutely there.
Oh, that's great. That's great. I enjoy the field trip, perhaps more than the talks. So,
Yeah.
okay. Well, thank you for this
Thank you.
opportunity. I appreciate it.
Thank you. And I think it looks like we've got 27 out of 27 voted on the poll.
Good.
I think I saw,
That's okay. I can turn mine off.